In the very first module of Precalculus Refresher course, we will talk about algebraic fundamentals. These are algebraic procedures that are absolutely essential for you to access a number of calculus concepts. We will start with something fairly straightforward, such as fractional arithmetic and various exponents, and move into simplifying expressions, factoring, and solving equations. We will, for a lot of these concepts, first talk about how this works on numbers, because that's the exact same way that it will in fact work on variables. Let's start with the simplest operation on fractions, which is multiplying. For fractions, we multiply across. So if I have two fractions, each with numerator and denominator, in order to multiply them, I simply multiply the numerators and multiply the denominators across. This is fairly straightforward. Again, this is the simplest operation of fractions. Let's see how this works on some numbers. So our first example here, 2/3 times 5/7. I will have 2 times 5 multiplying across the numerators, 3 times 7 multiplying across the denominators, or altogether 10/21. If you have a negative as one of in front of the fraction, you can decide to move it into the top or the bottom, but not both. So here, this is equivalent to saying that it's 2/3 times -5/7, which then allows me to once again multiply across as before, so -10/21. If you encounter a case like this one, 2/3 times 5, while we're trying to apply the same rule, notice here that 5 is not a fraction, so it's missing a bottom. One easy way to introduce a bottom is simply to say this is the same as 2/3 times 5/1, right? Any number is itself over 1. And now that I have a clear numerator and denominator, I can apply the same rule as before. So I'm going to end up with 10/3. And then finally, let's do this example just to see what can happen after we've done multiplying. 4 times 5 is 20. 3 times 8 is 24. Hopefully, you remember from years of experience in school that this is not the simplest this fraction can be. So there's something that we can do here to make this expression a little smaller, and that is to in fact somehow cancel out common factors within 20 and 24. So for example, we can divide everything by 2, so this will be 10 and 12. And then we can notice that 10 and 12 still have a common factor of 2. We can cancel that out to get 5/6. Now that 5 and the 6 don't have anything in common, this is the simplest expression that this fraction can be. So thinking about canceling the various things across the tops and the bottoms of the fractions, there's a couple of really important things you have to remember. You can only cancel something within a fraction if it is a common factor to both top and bottom. It has to be a common factor of the entire top and bottom. I cannot stress enough how important this is and how often students make this mistake of canceling just a part of top and bottom or something that's not actually a factor. So let's go through example and I will point out what one should and should not do. So this 24/30, clearly we have a common factors between 24 and 30, and you can decide what to divide by in any order you want to do this in. So for example, I can notice first of all that 24 and 30 both have 2 as a factor, so I can cancel out the 2. I will end up with 12/15. I can then notice that 12 and 15 have both a factor of 3 in common. I can cancel that out to get 4/5. Or alternatively, I could have first of all divided both top and bottom by 3, yielding 8/10, and then by 2, yielding 4/5. So my final answer is 4/5 no matter what. So if you're going to cancel something out, the order in which you cancel the factors does not matter, as long as they were always common factors on top and bottom. 4/3 times 5/8, this is the same example we've just seen before, but what I'm going to do now is instead of first performing the actual multiplication operation, I'm going to look at it and think for a second, is there something I can simplify in these two fractions before performing the multiplication? And I can notice that, of course, here, the 4 and the 8 have factors in common, specifically 4, so I can cancel out the entire 4, leaving 1 behind, and 8 will leave 2 behind. Once I've simplified, I can multiply across, so I'm going to have 1 times 5 and 3 times 2, 5 over 6, which of course is consistent with the 5 over 6 we've gotten before. So it is up to you whether to simplify before fully expanding the multiplication or after. Again, just as long as the operation was multiplication and the factors were factors of the entire top and bottom. Also be careful about what is left behind. So notice here when I've canceled out the 4, it's not that it just went away and became 0, it becomes a 1. 4 here is 1 times 4. This is a little more visible when the fraction only has one thing on top or bottom, so 2 over 18. We notice that I can cancel out a factor of 2 here, and I'm going to get 1 over 9. So be careful, 1 over 9, not 0 over 9, right? So canceling factors out will never result in the thing going away entirely. You still have a factor of 1 left in there. Okay, let's take a look at the second column here. Once we introduce the variables, it seems to be a much more difficult sometimes to see whether what you're trying to cancel is a common factor of top and bottom. So for example, here, what we see a lot of times in calculus is that students will be tempted to cancel these two 5s out. In fact, I'm going to do just that, what I see often on exams, and say no. No, no, no. Remember that in order to cancel, the things that you're canceling have to be common factors of top and bottom. This 5 is not a factor of the top. It is, in fact, a summand. So I cannot factor it out with, or I cannot cancel it out with anything. So before I do, I can try to maybe factor the 5 out from the top. I notice that 10x also has a factor of 5 in it. So if I first take out 5, what I will have left is 2x plus 1. Again, notice plus 1, not plus 0. All divided by 5. And once I do that, then notice that now this 5 is in fact a factor of the top, and it is a common factor with the bottom. So now I can cancel these two guys, and my expression will just become 2x plus 1. Okay? Similarly, in the next question here, h over h squared plus h. I cannot simply cross out these two h's because then I'm crossing out something that is not the factor of the bottom. Okay, so in order for me to perform anything here, I can try to factor out the h from the bottom and then see if I can then cancel anything out that's in common. I notice that indeed here I can factor out h from the bottom. We'll have h plus 1 left. And now I can cancel these two h's out. Notice once again that it's not that I have nothing left. I have 1 left and h plus 1 on the bottom. And this is as simplified as this expression can get. On this last question here, once again, do not do something silly like canceling out the 5s and then maybe even canceling out the x's after that, leaving you with the 5 alone. No, that is not how this works. And in fact, in this question, once again, I can see that I do have a common 5 in both terms on the top, but if I factor it out, I will have x plus 1 left. And then what happens here is that the top and bottom don't have any common factors. This 5 is a factor on the top, but there is no factor of 5 on the bottom, and I cannot cancel these two 5s because this 5 is not a factor. So in fact, in this case, there's nothing else I can do to simplify this any further. This is as simplified as this expression is going to get, okay? So sometimes things don't cancel out. Do not start canceling them out just because you feel like there's some arithmetic that needs to be done. Dividing fractions is the next simplest operation, and this involves what we call invert, or some people say flip, and multiply. So in order to perform division, let's say I start with a fraction a over b, and I divide by a fraction c over d. I leave the top fraction alone, and I will flip the bottom fraction and then multiply across. Now, the other notation that we use for division is the division sign. So let me first of all actually write this out. because this is actually something that you will see much more often rather than this sort of double-decker fraction here. So again, we leave the top fraction alone, and we multiply by the flipped version of the second fraction that was originally in the denominator. Here, we've now reduced this problem to multiplication, and I'm just going to multiply across the numerator and the denominator, yielding AD over BC. Okay, let's try once again how this works with numbers before we try it with variables. So 2/3 divided by 5 over 7. Again, I'm going to take my first fraction, leave it be, multiply by the flipped version of the second fraction, so 7/5. And now I can multiply across 14 over 15. I can also see if there's anything that I can cancel out. In this case, doesn't look like these two numbers here have any common factors. In the next one, 2/3, I'm going to multiply by the flipped version of the fraction. So once again, minus 7/5. And remember what we did with the negative before. You can join it with the top or the bottom, but not both. So you get to decide where you place it, or you can just place it in front of the resulting fraction altogether. So here I'm going to get minus 14 over 15. If you don't have the bottom on the thing that you're dividing or the thing that you're dividing by, as before, we can simply introduce a bottom to it. So 5 is the same as 5 over 1, and then multiplication or flipping and multiplying will result in 2/3 times 1/5, which altogether then will be 2/15. Excellent. And the last example here involves variables, but also various powers of them. So let's leave the first fraction alone, multiply by the flipped version of the second fraction. And then here, just like in one of the examples before, just like in this example here, I'm going to simplify this expression before I really carry through the actual multiplication. So notice, for example, that this x will cancel out with one of these x's, with an x squared. This y will cancel out with one of the y's here, and this z will cancel out with one of the z's here. So what I will have left is y times z all over x. Now we've talked about multiplying and dividing fractions. The other two operations that are left are adding and subtracting. They're a little more complicated because they involve having to deal with common denominators. So if you have two fractions, remember that you can only add or subtract them if they have the exact same thing in the denominator. And if they do, then it's fairly straightforward. Unlike the multiplication though, we add or subtract across the top, but the common denominator becomes one common denominator. So this is not going to be 7 times 7 here or 7 plus 7. It's just 7. So it's 2 7s plus 5 7s is 2 plus 5 7s. In this case, we can actually simplify this a little bit further. 7 over 7 actually turns out to be 1. Okay, so common denominators are key. We can in fact only perform this operation if we have common denominators. Common denominators are good, but what's even better are least common denominators. This is not necessary, but this will ensure that you're dealing with numbers that are as little or as small as possible, so you don't have to just deal with really big, clunky expressions. Let's take a look at this next question here. 2/3 minus 7/5. So obviously 3 is not the same as 5, so these don't have the same denominator, which means that I'm going to have to do something in order for their denominators to be the same. Notice that between 3 and 5, the least common multiple will be 15, which means that I have to multiply 3 by 5 and 5 by 3 in order to get to that. And this is another key part here. Whatever you do to the top of the fraction, you're going to have to do to the bottom of the fraction in order not to change its value. I like to remind my students that whenever you're doing evaluation or whenever you're doing simplifying is like putting makeup on. It can change the way that something looks, but it should not change the value, right? So if you're going to, you cannot just multiply by 5 on the bottom because then you're changing the value of the expression. If you multiply by 5 on top and bottom, it's essentially like not really doing anything. So it looks different, but it has the exact same value. So the second fraction needs to be multiplied by 3. So overall, 2 times 5 is 10 over 15, minus 7 times 3 is 21 over 15. And now that I have two fractions with the exact same denominator, I can combine them together. So 10 minus 21 over 15, or minus 11 fifteenths. Okay, so it's key to remember to multiply both top and bottom to gain your common denominators. Okay, let's take a look at another example here where there's seemingly no bottom for the second fraction. So 2/3 plus 5. Once again, if there's no bottom, simply introduce 1. Literally, introduce 1. 2/3 plus 5 over 1. Now we notice that our denominators are 3 and 1. So the least common one will be 3, which means that I have to multiply the second fraction by 3 on top and bottom. Here it's also easy to check. 15/3 is in fact 5. Now that they have common denominator, I can add them together. So I'm going to get 17/3. All right, let's take a look at some other examples here. 1/8 minus 1/4. So notice that, of course, 8 and 4, I can make the common denominator to be 32, which is a product of the 8 and 4, but then it's not the least one. So I'm going to be dealing with numbers that are larger than they have to be. Between 8 and 4, the least common multiple is 8. So that means that all I have to do here is multiply the second fraction by 2 on top and bottom, and I will get myself common denominators. Once I do, I simply subtract the tops and keep the bottom. Okay? In the next case, one of my denominators is z, one is 5, so they have nothing in common. I'm going to have to multiply each one by the other one in order to make them common. So multiply by 5 here and by z here. I'm going to get 5xy over 5z minus z squared over 5z. Now that they have common denominators, I can combine them together. 5xy minus z squared over 5z. Excellent. Similarly, you're going to see something like this here, where x and y, the denominators, have nothing in common. So you're going to have to multiply both pieces by the corresponding other denominator. So you don't have to worry here about trying to find the least common one. If they have nothing in common to begin with, then the least common denominator is simply the product of the two. All right, so let's see what happens when we try to combine these operations together. So we're going to have to deal with the order in which the operations have to be performed. And for that, it's important to remember your BEDMAS, or PEDMAS, I guess. It depends on how you remember it. Brackets, exponents, division, multiplication, addition, subtraction. Okay, so first we do what's in the brackets, then if there's any exponents, then we do that. Division, multiplications come next, and then addition, subtraction. Excellent, so let's take a look at this example here. I have a multiplication and a subtraction. Notice that multiplication comes before subtraction, so first I'm going to multiply these two fractions and then subtract the third one. I also strongly recommend, before you jump into doing any busy work, to just take a look at the expression that you're given and see if there's anything there that you can do right away to make it easier. So for example, notice here that I can cancel out these 3's before performing the multiplication because they are in fact common factors on top and bottom. I can also notice that this 2 over 6 has common factors on top and bottom, and in fact they can be canceled out to become 1/3. Right? I'm not going to do that. I'm going to show you what would have happened if you didn't notice those things. But do keep in mind that sometimes it's easier to, first of all, really take a little step back, see if you can simplify, and then go ahead through the operations. Now, if I were to multiply across first, it's probably worth it to put the brackets because it's easier to remember that whatever's in brackets you really should be doing first. So I'm going to have 6 over 12. And then I have minus 2 over 6. And then here, once again, I'm reminded of the fact that when I'm looking for common denominators, it's best to look for least common denominators, in this case it's going to be 12. So I simply need to multiply the second fraction by 2 on top and bottom. So I'm going to have 6 minus 4 over 12, or 2 over 12, and if I cancel the factor of 2, I'm going to get 1 over 6. All right, now if I have the brackets around here, then I have to perform what's in the brackets first as opposed to here. Sometimes the brackets are implied, sometimes they're explicitly stated. So I'm going to first of all subtract these two from each other. And here I will first of all simplify this 2 over 6 to be 1/3, because that will actually make my life quite a bit easier right away. Because notice that I'm going to have 2/3 minus 1/3. And whereas here, these two guys did not have common denominators yet, because that's how they looked, here they do. So here, I then can skip the step of doing the common denominators, because they are already the same. 2/3 minus 1/3 is 1/3. I can cancel the 2 3s, and I'm going to end up with 1/4. Okay, so once again, it's really worth it to take a step back and find yourself some things to simplify before doing heavy arithmetic. Between these two fractions, my denominators are a and a squared. So the least common one altogether will be a squared, which means that I can multiply the top and the bottom of my first fraction by a. And here, please be careful. I have to multiply the entire top and the entire bottom by a in order to get common denominators. So I'm introducing these brackets here just to showcase that and to notice that I have to actually factor this a into the entire bracket. In fact, let me just write the first step out like this. Adding the second fraction will give me the +1 that came from here. So this is my +1 all over a squared. If I decide to open the brackets now, I'm going to get a squared plus ab plus 1 over a squared. And that's as simple as that's going to get. We will see actually quite a bit of usage in taking two fractions and modifying them to be one big fraction in calculus, because this will really help solve various types of equations for things like critical points and whatnot when you're analyzing graphs using derivatives. This expression comes exactly from the derivative, from the definition of derivative that you're going to see very quickly into a calculus course, and you will have to simplify expressions that are exactly something like this. In fact, this is probably going to be one of the very first examples that you're going to see using the definition of derivative. So here, notice that I do have a sort of double-decker of a fraction where this is the main division sign. So the first thing I'm going to do is simplify the top of this fraction, which is a difference of two slightly smaller fractions. So if I have to bring these two together, I have to find the common denominators between them. They have nothing in common, which means that I'm going to multiply top and bottom by each other. So in this case, this first guy, I have to multiply by x, and the second guy, I will have to multiply top and bottom by x plus h. So let me write this out carefully. X over x plus h minus x plus h over, whoops, I missed an x. I said I'm going to write this out carefully and then made a small mistake myself. There we go, all over h. Okay, so don't forget this h over here. Great. Now my two things on the top do have the same denominator, so I can bring them together. Be very mindful of the fact that this minus is in front of the entire fraction, which means it's in front of the entire numerator, okay? So when I do bring them together, I'm going to have x minus x plus h all over x plus h, and then finally all over h. So I'm going to place my equal sign lined up with the main division sign here. Okay, now I can, so that's what I mentioned earlier, right? Like, be very careful about this minus here. It's not just minus x plus h, it's minus the entire thing on top. So this minus affects the entire bracket, which means it has to be factored into the entire bracket. So I'm going to have x minus h over x plus h all over h. Okay, well, this is kind of nice because x minus x cancels out. And what am I going to have left here? Running out of room quickly, which is not surprising. This is always a long example. Minus h all over x plus h all over h. Okay, and here is where we're going to utilize our practice with dividing fractions. This is my main division line. So I'm dividing this top fraction by this bottom fraction. Now the thing on the bottom isn't quite a fraction. So remember, to divide fractions, I'm going to keep the top the same. So minus h over x plus h times, and then I have to flip my bottom fraction. But right now it's not really a fraction. Remember what we've done when that happens? I'm going to introduce the bottom to it, over 1. That way I can see what it becomes when it gets flipped, which is 1 over h. Okay? And then here, now, I can also see that this h on the top and this h on the bottom can cancel out because they are, in fact, factors of both top and bottom. And once I do that, I have my final expression, which is minus 1 divided by x plus h. Okay? So this entire expression is actually equivalent to minus 1 x times x plus h. And this is, in fact, how you will compute the derivative of a function 1 over x, the reciprocal function. Okay? I'm not going to go through this example because it's actually quite similar to what we've just done above, but I do encourage you to practice with a little bit yourself just to see how this works out, because this is really good practice too with all of the operations combined in one place. At the end of this unit, please take a look at the webwork assignment called Module 1A for various practice with operations on fractions and combining operations. And this will include operations with fractions that are just number fractions, as well as fractions that have variables in it.